So today I'm not the guy running around with the laptop. I hope. I may interrupt with some technical issues, but it won't be the computer, but perhaps like a minus sign mistake. So it's my great pleasure. Rest assured. So it's my great pleasure to introduce the first speaker of this morning session, Stephen Carlip from the UC Davis. So he's worked on many topics in quantum gravity, and he has the distinctive ability to overview our field. He has written numerous review papers on, say, 3D quantum gravity, on space-time foam, on thermodynamics of black holes, and now he will review for us the causality in quantum gravity. And we're very much looking forward to hearing about this. The floor is all yours.
Okay, thank you. So the organizers asked me to give a review on causality in quantum gravity, and I told them I would do my best. This is a tricky subject, partly because it's very broad, partly because it's not understood very well, and in particular for this talk because I don't understand it very well. So if you want to come up with questions to stump a speaker, this is your chance. So let's start at the very beginning. Back in kindergarten, when we first learn about relativity, we are taught that Einstein unified space and time into a single space-time. And of course, at some level, that's correct. But it's also potentially misleading, at least to kindergarteners, because space and time are still distinct, even if there isn't an absolute space or an absolute time. Space-time is characterized, at least classically, by a Lorentzian metric. And that means that the metric picks out light cones. Those determine local causality, which extends to a causal structure on the whole space-time. And that causal structure is really central to many, maybe even most of the important developments in general relativity in the past 50 years. Everything from singularity theorems and cosmic censorship to almost everything we know about black holes. After all, a black hole horizon is defined in terms of a causal structure. To asymptotic structures of asymptotically flat or de Sitter or anti-de Sitter spacetimes, or on a more ordinary, less mathematical level, the propagation of gravitational waves, all come around to causal structure. In fact, one can say a little bit more than that. There is some sense in which the causal structure is most of the space-time geometry. Specifically, if you have a causal space-time, think of that as just a space-time with no closed time-like curves, though there are some subtleties. But if you have a causal space-time, then there are some basic theorems that tell you that the topology and geometry are both completely determined by the causal structure and the volume element. Roughly speaking, the causal structure determines the metric up to a local scale factor. The volume element determines that scale factor. So depending on how you're counting, the causal structure is 9/10 of the metric. Or if you want to factor out diffeomorphisms, it's still 5/6 of the metric. So this is a beautiful classical picture, and then, as usual, quantum mechanics comes along and spoils things. In particular, we expect that quantum fluctuations will blur out the causal structure by making light cones fuzzy. As far as I know, this idea was first suggested by Pauli in 1955 in a remark at a relativity conference, and very quickly taken up by Klein and Landau and others. Very soon after that, Deser and DeWitt started to look seriously at whether this fuzzing out of light cones, blurring of causal structure, what kind of effects that would have on quantum field theory. Now, there are a number of ways of looking at this. One first thing to notice is that gravity is attractive, so positive energy fluctuations make light converge. So they narrow light cones. This picture is actually not quite right. The tip of the dotted light cone should be the same as the tip of the outer light cone. But so positive energy fluctuations, one could argue, don't interfere with ordinary causality in the sense that they don't allow for travel faster than light. On the other hand, we're talking about quantum physics here, and in quantum field theory, field fluctuations can have negative energy as well. There are some kinds of average energy conditions that sometimes could be interpreted as saying that on the average, quantum fluctuations don't produce faster than light travel. But on the average is really not good enough for a question like that. You can also look at this in the context of effective field theory, where the effect of quantum fluctuations is abbreviated as the addition of higher derivative terms in the action. And in that case, there are some nice results about the signs of various coefficients that are required in order to prevent violations of causality. This puts some limitations on what kinds of effective field theories make sense have sensible ultraviolet completions. Again, though, this is basically a low energy consideration, and it is fairly easy to show in effective field theory that when you start to get to high energies, you get causality violation. For example, if you look at the effective field theory predictions for Shapiro time delay. In fact, one can say a little bit more than this about the effect of quantum fluctuations on causality and light cones. Quantum fluctuations of quantum fields are actually very highly non-Gaussian. They have a most fluctuations are negative. There is a strict lower limit, though, and there is an infinite positive energy tail that falls off more slowly than exponentially. Now, we don't know how to fully treat this in quantum mechanics, but if you look at these fluctuations and you approximate them as stochastic fluctuations, you can look at what they do to light cones. And the answer is related to this fat tail. You run into a phenomenon called gambler's ruin. The gambler's ruin theorem is basically the theorem that if you are betting against an opponent who has infinite resources, you always lose in the end, no matter how good the odds are for you. That's what happens here. Although most of the fluctuations are negative energy and actually bring light cones to a sort of equilibrium, sooner or later, one of these very high energy positive fluctuations is going to come along and collapse light cones. And in simple models, for instance, in 2 dimensions where this can be done exactly, you find that this happens, that for Planck scale fluctuations, this happens on the order of 100 times the Planck time. So quantum gravity, at least at the Planck scale, is certainly messing with causal structure. In fact, at least in principle, you can construct a superposition of different causal structures by hand. This is from a paper by Zick and collaborators. The basic idea is very simple. You start with 2 observers, Alice and Bob, who synchronize their clocks at some fixed initial time slice and agree that after a proper time, tau A, Bob will flash bulb, and after a proper time, I'm sorry, A is Alice. Alice will flash a flash bulb, and after time B, Bob will flash a flash bulb. These are nice diffeomorphism invariant statements. Now suppose that you put a very heavy mass next to Bob after this experiment has started. Then Alice will see Bob's laboratory time dilated, which means that she will see a delay before Bob flashes his flash bulb, which can be long enough that it puts event B, Bob's flash, to the past of event A, Alice's flash. Suppose you take the same mass and put it next to Alice, then you get the same result, except that the causal order is reversed. So now take the mass and put it into a superposition of a state where it's next to Alice and a state where it's next to Bob. That will give you a superposition of the causal orders of the 2 events, of the 2 flash bulbs going off. We can't do this in the lab yet, but as we've heard, the Vienna group and others are working very hard on putting significantly large masses in superpositions of positions at significant distances. This will come. So why is this bad? Well, the most basic answer is that it wrecks quantum field theory. One of the most fundamental axioms of quantum field theory is microcausality, which is the statement that if you have 2 operators whose support lies on space-like separated points, then they commute. They can't affect each other. And this is really part of the fundamental basis for quantum field theory as we understand it. For example, this is the key ingredient that goes into the derivation of the analyticity properties of the scattering matrix. But if we don't know whether points x and x prime are space-like separated or not, or if we have a superposition of spacetimes where they're space-like separated in some and not in others, we basically just don't know how to do quantum field theory in a setting like that. And to the extent that we can think of quantum gravity as a fancy quantum field theory, this is part of the reason that we don't know how to do quantum gravity. This fuzzing out of causality is also very closely related to what are commonly called the problems of time, as discussed in Kiefer's talk. For example, it's commonly said that in order to make sense of probabilities in a quantum theory of gravity, you have to normalize them, which means normalizing them at a fixed time. You want to say that there's a probability of 1 that your electron is somewhere in the universe at a fixed time, not that it's ever somewhere in the universe. But if you think about this, the reason a fixed time is important is precisely because of causality. It's because you want to normalize probabilities on a hypersurface in which you know that the electron won't be there twice. If you don't understand causality, then you don't understand the first step even towards what it means by saying at a fixed time. And of course, that also means that you don't understand what unitarity means, because unitarity is a description of what happens when you move from one fixed time to another fixed time. So again, we don't know how to do quantum mechanics. So that's why this might be bad, but there are other reasons that it might be good. And these go back again to Pauli in 1955. If you look at the divergences in ordinary quantum field theory, we usually think of those as coming from infinite momentum exchanges. But if you translate that back into position space, the divergences come from fields at points that are null separated. And so if your light cones are fuzzed out, then maybe those divergences go away. This was first taken up by DeWitt in the early 1960s and then worked on by a whole series of other physicists who basically, from first principles in ordinary quantum field theory, said, let's look at a divergent diagram and then sum up an infinite number of diagrams that include gravitons. And they found that for certain infinite series of diagrams, the divergences of the individual diagrams disappeared, and you did get finite results. Now, this is an intriguing idea. It more or less faded out of sight because it's one thing to be able to show this for some particular subclass of Feynman diagrams, but you really need to know it for all Feynman diagrams. And of course, we don't know how to do that. Richard Woodard has pointed out that the cancellation here that these people have seen involves cancellation between different orders in the perturbation expansion, and what might be needed is some systematic reorganization of perturbation theory in quantum gravity, but we don't know how to do that. So other people have approached this more phenomenologically. You can just take your propagator in quantum field theory and by hand stick in some fuzziness, either stick in a minimum length. The first expression there is from a paper by Padmanabhan, or smear out the propagator with some smearing function f. The second expression is from a paper by Ohanian. There have been a whole series of phenomenological models like this, and they all give more or less the same result, that in fact fuzzy light cones might very well get rid of divergences in quantum field theory. There are a few other reasons that you might like the idea of some sort of mild breaking of causality in quantum gravity. For one thing, it allows topology change, which, depending on your personal point of view, might be a good thing or a bad thing. But there are some basic theorems that essentially say that if you have a Lorentzian metric, that is causal. I'm sorry, if you have a Lorentzian metric, then change in spatial topology requires either singularities in the metric or closed time-like curves, that is, violations of causality. So if you want to allow such changes, the easy way to do that is to allow violations of causality. This might be important in the answer to the problem of the question of black hole information loss, where some of the recent work gives a very important role to wormholes and other forms of non-locality, which in turn require this breakdown of causality. Also, there might be observational consequences. This at least gives us something that we can look for. For example, in loss of coherence of starlight and breakdown of interference patterns from light from distant galaxies. I'll come back to that a little bit at the end. So suppose that you believe this, that quantum gravity somehow allows superpositions of different causal orders, or the path integral includes paths with different causal orders, or quantum fluctuations mean that your light cones are not a fixed structure. One of the first questions you have to ask is whether it's even possible to do quantum mechanics in that setting. And certainly you can't quite do quantum mechanics as we ordinarily do, because in ordinary quantum mechanics, the way you treat two systems that are space-like separated is very different from the way you treat two systems that are time-like separated. If you have two space-like separated systems and you want to write a wave function, you write down a product wave function or a superposition of product wave functions, but wave functions on a product of two Hilbert spaces. If you have two systems that are time-like separated, that is, if you have a single system at one time and then another, you write that in terms of a single Hilbert space and some operator that tells you how to get from your initial time to your final time. So there's been a lot of work. This is one of the areas where I'm very definitely not an expert, so this is an outsider's summary of this. There's been a lot of work, starting with Hardy in 2005, looking for reformulations of perhaps slightly generalized quantum mechanics in which you treat space-like and time-like separated systems on an equal status, what's sometimes called causally neutral quantum mechanics. There's also been work from more within the quantum gravity community, for instance, by Eckel on the path integral version of this kind of idea, the general boundary formulation. The answer is that it can be done. There are a number of different approaches, but that are, I am told by experts, more or less equivalent, that allow you to write down this slight generalization that reduces to ordinary quantum mechanics when you have a single causal order. When you do this, you find that there is an analogy to Bell's theorem, that there are certain inequalities that are that must be obeyed if you have a fixed causal order, but that can be violated if you can have a superposition of causal orders. Now, the way that I've stated this, I haven't referred to gravity at all. And in fact, there are proposals and even claims of implementation of this kind of structure in the laboratory, where you simply have some qubit that can go through 2 gates, and you can choose to have it go first through gate 1 and then gate 2, or first gate 2 and then gate 1. You can put a quantum control system that then allows you to put a superposition of those orders. So that looks sort of like a superposition of causal orders. This is a little mysterious, though, because this is all happening in a lab in a very nearly flat space-time where there is an outside definition of causal order that doesn't depend on how you set up your quantum system. And my understanding is that there's some controversy about this, but there are claims that look at least completely plausible to me, for instance, by Villacini and Renner, that say that you cannot, in fact, set up this kind of superposition as a superposition of pure states, at least, in the laboratory. This is without gravity, though, and with gravity, presumably there is nothing to prevent something like this from happening. So this is still somewhat of an open question, as I understand it. There's still room for surprises. For instance, there is this beautiful thought experiment by Balencia, Wald, and collaborators that looks as if it allows you to use gravity to violate causality. The basic idea is simply that Alice takes a mass, puts it into a superposition of positions, and Bob, at a space-like separation, decides either to measure the gravitational field, which would then determine which of those positions the mass was in, or decides not to, in which case Alice's particle remains in the superposition and she can recombine the paths and look for interference. It turns out that there is a conspiracy of 2 quantum gravitational effects. On the one hand, there is the quantized emission of gravitons from Alice's particle as she moves them apart or together. And on the other hand, there's an uncertainty in the maximum precision that Bob can make his measurements from gravitational fluctuations of the space-time. These 2 things together combine to just barely prevent this kind of experiment from violating causality. So there's something deep in quantum gravity that really likes causality, but I don't think it's understood what that is. So now let me turn to a few specific examples of how causality comes in, or causal structure comes in different approaches to quantum gravity. The starting point is causal set theory, because that's an approach which is fundamentally built on causality. So the idea here is that if you want a discrete model of space-time and you want to start with causality, with these theorems about the causal structure plus volume determining space-time, then there's a natural form of discretization, which is to start with a discrete set of points, but points that have a causal order, where x precedes y mathematically is interpreted as x is to the causal past of y. And then you add 2 features. You add a feature of no closed time-like curves. There are various ways of doing this. The simplest one for me to understand is to simply require that no point is in its own past. And then you put in a discreteness requirement, which Samadhi Surya talked about, gave a little demonstration of in her talk. You simply say that the causal diamond, the future of one event intersected with the past of another, always has at most a finite number of points in it. So that gives you the basis for causal set theory. And if you start with a space-time and then use this picture to form a discretization, a discrete causal set, then we understand the resulting topology and geometry fairly well. That is, we understand the causal set determines some discretization scale, but at distances above that scale, we understand reasonably well how from the causal set to reconstruct the volume, the dimension of the space-time, the volume, the curvature, the coarse-grained topology, as well as nice things like D'Alembertians and Green's functions. If, on the other hand, we want to think of causal sets as being fundamental, it looks like a complete disaster. Almost all causal sets, and I mean this in the strong mathematical sense, at least in the limit that the size of the causal set goes to infinity, almost all causal sets are these peculiar things called Kleitman-Rothschild orders, which have only 3 moments of time. That is, if you start at one point, you can go at most 2 steps to the future before the causal set ends. That's not our universe. It's not a space-time at all. You might hope that those are some sort of weird exception, but if they're not, if you throw those out by hand, almost all remaining causal sets have only 2 moments of time. You throw those out, almost all of the remaining causal sets have only 4 moments of time, and so on. So the reason that I'm mentioning this is that a recent result by Peter Carlip, Samadhi Surya, and me, which is being written up almost as I speak, we've shown that if you use the standard Einstein-Hilbert action with the appropriate discretization to make sense for causal sets, then the path integral, or strictly speaking, the path sum, very strongly suppresses these non-space-time-like layered causal sets. Very strongly means by a factor of 2 to the minus n squared, where n is the number of points in the causal set. So for a region of a cubic centimeter times 1 nanosecond, that's a factor of 2 to the minus 10 to the 260 something. So that's pretty serious suppression. So let me emphasize, though, and I'll return to this later, that a classical causal set has this idea of classical causality built in. But if you're looking at a path integral or a superposition of causal sets, you get causal sets with different causal orders. There's nothing different here for causal set theory than what I was saying very generally for quantum gravity. One thing I'll mention in passing, again, this is something that I'm not an expert on, but there is a nice argument by Bianchi and Martin Dussaud that if you have a simplicial complex or a spin foam, that naturally contains a causal set structure from looking at the one skeleton, that is just looking at the lines connecting the interiors of neighboring simplices. That comes with a natural direction. There are nice consistency conditions that make it into a good causal order. And this has interesting implications that I don't understand for spin foam theory. Now, let me briefly mention one other particular case where causal structure has been important and interesting in a very different context, which is holography, and in particular, the ADS-CFT correspondence. So in the ADS-CFT correspondence, you have a boundary at infinity that has an ordinary quantum field theory with no fluctuations of the metric, and so with an ordinary fixed causal structure. And that quantum field theory is supposed to be equivalent to a theory of quantum gravity in the interior of space-time, of the asymptotically anti-de Sitter space-time, so in the bulk. So this leads to interesting threats of contradictions. You're supposed to be able to get the quantum field theory at the boundary as a limit of various quantities in the bulk, quantum gravitational quantities. But in the bulk, you can include, and in fact you have to include, metrics in which points that are space-like separated at the boundary can connect to each other along time-like curves in the bulk. It's easy to write down metrics that do this, and there's no reason that they should be excluded from the bulk path integral. So this looks as if boundary causality is inconsistent with the bulk theory. So there's been a very nice analysis of this by Gary Horowitz and his students, who point out a kind of subtle detail, but that turns out to make a huge amount of difference. So first of all, this condition of boundary causality is very strong, because it says not only that the commutator of two space-like separated operators at the boundary has to be 0, but that if that commutator appears in an arbitrary correlation function with any number of other operators, it still has to give 0. That seems to be a very hard condition to obey. But what these authors pointed out is that writing a commutator as a path integral is tricky, because path integrals automatically give you time-ordered products of operators. And so if you have operators that are time-like separated, the path integral will give you the product of those operators in a particular order. And you have to do something funny to get the out-of-order product in order to define a commutator. Specifically, you have to sort of integrate forward in time and then backward and then forward again. And that changes the manifold that you're defining your path integral over into something that they call a time fold, where it folds around at some time. And what they showed is by carefully analyzing the boundary conditions for time folds, that the contradiction goes away, that in fact you can't connect the boundary points through the bulk in a way that gives you a non-zero expectation value for these commutators. So that's another interesting place where quantum gravity seems to conspire to give you causality where it would seem to not be there. So a couple of brief comments about causal structure. Elsewhere, we can look at the general path integral And as Bianca Dittrich told us in a really beautiful talk at the beginning of the conference, there is a lot of progress now in trying to understand path integrals using Lorentzian metrics, so in ways that at least admit that there is a causal structure. Now, there's an interesting old issue here that, as far as I know, remains unresolved, that goes back to Claudio Teitelbaum's thesis. Suppose that you look at a Lorentzian path integral in Hamiltonian form. So the ordinary Einstein-Hilbert action in Hamiltonian form looks like pi q dot, the usual pq dot term, plus some constraints. And let's look in particular at the Hamiltonian constraint, which is supposed to be at least the equivalent of the generator of time reparameterization, sort of diffeomorphisms involving the time direction. So if you look at this path integral, if you integrate n, the lapse function, from minus infinity to infinity, that gives you a delta function of the constraint. That's nice. That tells you that the only paths that come into the path integral are paths that obey this constraint. That's good. The problem is that the lapse function geometrically is the thing that defines proper time intervals, that d tau is roughly just n dt, where t is your standard, some standard time coordinate you've chosen at the beginning. And if n can come in with an arbitrary sign, then you can have paths that move forward and then back and then forward. In other words, you have paths in the path integral that very obviously violate any sensible meaning of causality, that very specifically move backwards in time. There's an easy alternative to this, which is to allow the lapse function only to run from 0 to infinity. That means that you're only looking at paths that are moving forward in time. If you do that, though, then the integral over the lapse function doesn't give you a delta function anymore. And while configurations that don't satisfy the constraints are suppressed, they're only suppressed in the same way that any other configurations that aren't classical solutions are suppressed. So this is a mystery. Do we want to not impose causality but impose the constraints strongly? Do we want to only impose the constraints approximately but keep causality? I think the answer is basically unresolved. So we've also seen these issues of causality come up in other contexts already in this conference, in the current attempts to transfer what we know about asymptotic safety to a Lorentzian setting, where there were some interesting results in the parallel session about state dependence of the renormalization group flow in the infrared if you have a Lorentzian renormalization group. Some very nice work on the Lorentzian spectral function. There is causality in causal dynamical triangulations, which I'm not going to try to say anything about because that, I believe, is the subject of the next talk. So let me conclude. So when my son was in elementary school, he decided that a good working definition of science was that science is a state of confusion. This is not a bad definition, because the purpose of science is to discover new things, and you're not going to discover anything new if you aren't confused about what you think you already know. So that's where I think we are in terms of causal structure in quantum gravity. There is a lot of interesting work on ways that individual classical spacetimes, or classical-like spacetimes in a path integral or a superposition, can be causal, how causality can be put in explicitly in everything from causal sets to boundary unitarity. Very interesting work in that area. But none of this answers the question of why superpositions of causal orders aren't completely obvious around us. Causal order is something that seems pretty physically fundamental. But as I've said, there is nothing obvious that prevents you from having superpositions of causal order or having fluctuations in causal structure. And so the question is why this is so strongly suppressed in observation. I don't know the answer to that. Well, I'm confused. And I'm not sure that anybody does. There are certainly arguments that say that, there are certainly settings in which there are good arguments that say that violations of some background causal order can be suppressed in the path integral. Dietrich and Asante have talked about that in the discrete context, for instance. But it seems to me that it takes awfully strong suppression for everything that we know about classical general relativity to work so well. So I want to leave this in part as a challenge to the quantum gravity phenomenologists. There has been a lot of work about how we would see things like violations in Lorentz invariance. There has been, I think, less work on specifically how superpositions of causal order might show up observationally. And perhaps it's just that my intuition is wrong and that these are very hard to see, even though they occur in principle. But I think that this is something worth exploring in much more detail. And so on that confused note, I will stop. Thank you.
Thank you, Steve, for this beautifully clear review of our confusion. So I think you've also provoked quite a bit of discussion, and we have time for several questions. Let's start here in the back with Christoph.
The causal structure is a property of the metric, just like the rest of geometry. Now, of course, if you do a functional integral over metrics, you have obviously an integral over very different causal structures. So the superposition of causal structures is there whenever you have a functional integral over the metric. But the question is, where could you observe violations? Let me just have a simple picture. At the end, you have a functional integral, you compute the effective action, you have field equations, and if you find, and the field equations are, of course, for the expectation value of the metric. So if the field equation leads to a metric that has a reasonable causal structure, then it's very hard to see where you could observe possible violations, because you would have to go beyond the expectation value of the metric. You would go to fluctuations, higher order correlation functions, or something like that. But it seems to me that when you have a situation where the solution of your field equations has an acceptable causal structure, then you are, for most purposes, more or less done.
So the question is how exactly what most purposes means in this context. And yeah, I agree. Now, there are certainly situations in principle in which you can have macroscopic superpositions of causal structures.
Chris, please take the microphone if you want to comment.
All that is, of course, if you think about a functional integral, you can, of course, once you have the quantum effective action, describe all observations by correlation functions.
Right.
Even, superpositions of atoms, of clocks, and so on, it's all, at the end, goes back to correlation functions. So the question is, in what type of correlation functions could one observe violations of the causal structure if one has already a situation where the expectation value of the metric has a very acceptable causal structure? And that is not obvious to me.
Yeah. I agree that it's not obvious, but it is. I guess the only thing I would add to that is that the fact that causality is observed to play, the fact that causality plays such an important role in so many parts of classical general relativity suggests to me that even fairly subtle violations ought to be visible. I mean, a standard example would be that if you have light coming from a distant galaxy that's traveling through a space-time with a superposition of metrics, you should expect a superposition in the times of arrival of photons. And certainly you can look at the expectation value and get a nice answer that agrees with what we see. But you can then ask, are there interference effects, or in this case, blurring of interference effects, because of the fact that the photons are traveling in a superposition of classical metrics with different causal structures. As I said, I don't know the answer to this. I think it's something that's begging for more careful analysis.
Okay. So maybe I can shortly comment on this question. So the situations like this on the slide, the gravitational quantum switch. So of course, like the example with the Earth is just a thought experiment, so it's not something that we aim at realizing anytime soon in a laboratory. But in principle, this could be realized by putting a mass in a quantum superposition, like the ones that Markus Aspelmayer has in his lab. And that is exactly a situation in which you cannot approximate the stress energy tensor with its expectation value. So basically, the situation that would realize, so if we want to take an effective field theory description of that type of situation, we would have to linearize Einstein's equations, and then we have a quantum perturbation on top of, say, Minkowski, and then the source is prepared in a quantum superposition of two macroscopically distinguishable states. That in quantum theory, that means that they're orthogonal one to the other. And then basically you would have for, so we also have a paper with Ling Chin and with Carlo Rovelli, where we have exactly the description in linearized quantum gravity of this situation. And then what you assume is basically for each classical position of the sorts, then you effectively, the state of the sorts is an eigenstate of the current of the gravitational field, and you can do exactly the same for electromagnetism. And then you superpose these two solutions. So now, coming to the switch, this is of course, so the element that you take from this description is that you can linearly superpose these two solutions and that you can effectively treat the gravitational field as classical in each amplitude of the superposition. And then you are able to superpose the paths of the two photons for each classical position of the mass. Then there is another whole story that comes from a more quantum information perspective, that is the process matrix formulation in which this gravitational quantum switch is formulated, that is instead something that does not require starting with space-time at all, as you actually mentioned in your talk. And then it's just about logical compatibility of signaling relations between two laboratories, A and B, in which you can perform local operations. And then this would be a structure that allows for superposition of causal orders without actually ever violating any causality principle. So you basically, just by imposing conditions on the probabilities, you can rule out logical paradoxes. So, and you don't have to do that by hand. So this is just to clarify a bit the framework in which this is, this can be understood. But thank you for your talk. I really enjoyed that.
Yeah. Can I just?
Yes, so this is a very nice discussion. Perhaps I can ask whether there is a question from a different corner of the room? Or we can just continue this discussion. It's fine with me. We're a democracy here. So yes, go ahead.
I just want to add a quick comment. Is that the definition of event in relativistic community and in quantum information is actually different. So here, this is pointed out very in a paper by Villassini and Renato Renner. They point out very clearly that. So for causal set and for gravity, quantum gravity, we treat a point on the manifold as an event. But here, like in this paper in the gravitational switch, each event is like a local intervention relative to some reference frame for the local laboratory. So I think it's like very important to discuss about the indefinite causality when we distinguish these two concepts.
So do we have any questions from the chat, perhaps? No? Okay, very good. We can have a last. Okay, go ahead.
Just to answer this question, let's be a bit more precise. I mean, the field equation for the mean value of the metric has on the right side the mean value of the energy momentum tensor. This is just an identity, you cannot change it. So you can now say that this is not enough, but then you have to go to correlation functions, and you have to tell me which type of higher correlation functions you are observing in your experiment that goes beyond that. And then one can judge if one could expect there a possible violation of causality or not, or something like that. But I think it has to be phrased in this way. Otherwise, it's too, just to say the energy momentum tensor is a superposition. Well, you have to think what you do. I mean, the field equations are for expectation values, and that's definitely the expectation value of the energy momentum tensor on the right-hand side. That's just a mathematical identity if you go to functional integrals. And you have to reformulate things into higher correlation functions, 2-point functions, 3-point functions, I do not know, in order to be able to judge really what this, for me at least, what this experiment could probably tell us.
Okay, so thank you very much for this comment. Maybe, do you want to comment further on this? No?
No,
okay.
I agree with, I don't think there's been any contradiction in what people have said, and as far as I can tell, I agree with all of it.
Okay, so let's give Steve another warm round of applause.